Hello everyone, and welcome to our presentation on SpinoSense, a way to track and record patient pressure data. So imagine this. Imagine the scene, sirens are blaring their loud trill, first responders are rushing back and forth from the accident site. Everything is in chaos as they lift the patient up onto a spinal board. In the rush of the moment, they transport the patient from the site of the incident to the hospital, and immediately emergency care begins. Health professionals are working against the clock to treat the patient, because in trauma care, every second matters. In the heat of the chaos and confusion, the main priority is patient care and immediate treatment. One of the most crucial parts of trauma care is the immobilization of the patient's spine. This is done using a spinal board, where a patient is laid out on their back and strapped to the board. It is important to monitor the patient's movement throughout the whole extrication and transportation process to the hospital to reduce any extra damage to their body. However, in how much time do first and second responders have to continuously monitor the patient? And if the patient is not monitored, what are the consequences to their health and treatment? So improper monitoring or lack of monitoring of trauma care patients on spinal boards can, in fact, be more detrimental to their health in the long term. The standard design of spinal boards used by lifeguards, paramedics, and other first or secondary responders have limitations. First, they are not capable of complete spinal immobilization, meaning that even the slightest shift in body weight could have potential harmful consequences. Second, spinal boards are designed as a one-size-fits-all. Obviously, not everyone has the same body size, and as such, monitoring patients of different body weights and physical disabilities are not considered in spinal design. And finally, the pressure distribution on the board might not be even throughout the entire transportation process, leading to imbalances in pressure applications in the already injured patients. This can result in the formation of pressure ulcers. In fact, 75% of trauma patients develop a pressure ulcer that will need long-term care and treatment. Of this percentage, 63% experience pain from a pressure ulcer, and 38% experience severe pain requiring additional care. These patients are already dealing with the burden of care that comes with being in a severe dangerous trauma accident, so the formation of a pressure ulcer could be detrimental. And so this leads us into our problem statement. So our need is to continuously quantify the spinal immobilization and pressure distribution of a trauma care patient on a spinal board in order to inform first and second responders during the transportation of the patient from the site of trauma to the hospital.
Now we'll talk about some of the key design criteria of our project. So our first key design criteria is that we're able to handle up to 4 hours of pressure data. And this comes from the literature where we determine that pressure ulcers tend to develop within 1 to 4 hours of a patient being on the spinal board. And it was very unusual for a patient to be on a spinal board for greater than 4 hours. So we felt that this was a reasonable time frame that would fit most standard cases. Our second key design criteria is that our design does not interfere with standard first aid workflows. So to accomplish this, we worked closely with our stakeholder to identify what the standard first aid loading procedure was for patients onto the spinal board, and identified zones where we could and could not add components onto the board to ensure that there was absolutely no interference with the caregiver's method of getting the patient loaded onto the spinal board. Our third key design criteria is provide reasonable sensor tolerances. So in this case, we chose plus or minus 10% from the true calibrated weight. We felt this is reasonable given sort of the budget restrictions that we had and the quality of sensors that we could purchase. Further iterations would just simply have higher precision sensors that are just going to be more expensive. Our final key design criteria is to maintain reasonable patient comfort. So the board is already not designed for patient comfort or weight distribution, which is where the problem of pressure ulcers come from in the first place. So what we wanted to do was to avoid as many components on the patient side of the board as possible, and where they were on the patient side of the board, we wanted to ensure that they fit as flushly and as smoothly as possible to avoid any sort of outcroppings which could serve as further points of pressure ulcers.
Our project starts with a simple spinal board used in emergency paramedic situations, where we add pressure sensors to detect any prolonged injury. Places on the front of the spinal board were marked for significant anatomic locations. These locations were determined to have the most significant pressure applied to them during use. The back of the spinal board would be used to house all of the circuitry and Arduino that is required for the design. 4 sensors were chosen for this project based on the surface area of the sensors and the amount of weight that could be sensed upon them. The 4 sensors were then placed on significant anatomic locations that were known to cause the most amount of stress and develop the most amount of pressure shores during use of the spinal board.
Here's an overview of the back of the spinal board, which hides all our circuitry and keeps it out of the user's way. Looking closer, we have a lot of wiring connecting multiple PCBs soldered to many different electronic components and the Arduino. Arduino provides 5-volt power, ground, analog input pins for the sensors, and digital output pins for the LEDs. The PCBs, or printed circuit boards, were used to connect our circuit components and have a secure and permanent place for our resistors and capacitors. Each sensor required one 100 kiloohm resistor and one 100 microfarad capacitor. As you can see, the circuitry is well attached and the board can be flipped easily. Here's the last PCB soldered to our 6 indicator LEDs. To start using the smart sensing spinal board, first emergency personnel would adjust the patient so they are properly aligned with the sensor placements. As the patient lies down, high pressure spots will light up on the LED board. This indicates pressure is above the thresholds for the middle sacrum area. Medical staff then adjust the patient so their middle sacrum is no longer at risk and the indicator light will turn off.
Here we have the graphical user interface that was built for our product. Its use is to provide insight to clinicians and paramedics about the patient over the course of use on the spinal board. While the patient is placed on the spinal board, the Arduino is continuously collecting data from each of the pressure sensors, and what is seen on our graphical user interface is each of the data of the sensors collected over time with recordings in the newtons. Other key metrics that were included into the GUI was the total time placed on the board, as well as the total time in above the acute pressure threshold, as well as the chronic pain. This allows the paramedic to readjust the patient in real time, as well as provides valuable insights to the clinicians once the patient is transported into a safe location.
Finally, we'll talk about our future plans and applications for this project. So our first future plan is to increase the weather and conditioning hardening of our project. So spinal boards are often used in areas with extreme conditions. Future designs would need to be both water, heat, shock, and cold resistant in order to be used alongside the diverse settings in which spinal boards are also used in. Secondly, we need to improve our sensor precision and the total count of sensors on the board. Future designs would incorporate an array of highly precise pressure sensors, which would alleviate the need for more precise patient alignment and provide caregivers with higher quality data. Finally, a future plan we have for this project is to inform health regulation decision-making. So future collected data can be used to help draft new health regulations around spinal board design. Currently, there's a lack of data in monitoring how patients are handled and carried in spinal boards. The data our design collects can help fill this information gap and allow for better informed designs of future boards.